Hello and welcome back to the third part of the third week. Here we are going to be taking yet another approach to the longest increasing subsequence problem, and this time we are going to dive right in because we have already seen a fair amount of background with respect to the problem, and we already have one algorithm that solves it completely. But I just want to show you a different approach and use this as an excuse to talk about how you want to think about proving the correctness of your recurrences. Okay, so remember that we are given as input an array A of integers. And one thing I want to emphasize for this approach is that we are going to be thinking about where the optimal solution starts. Okay, so I don't know where it starts, but it must start somewhere, right? So if for each location I in the array, I knew what was the length of the longest increasing subsequence that started at A of I, then my final answer is just going to be the largest of these numbers, right? So let's say that dp of I stores the length of a longest increasing subsequence that starts at the ith element of the array, right? And again, let's go through our checklist and figure out if these values are useful for us to store, and that do they lead us to the final answer. And indeed, as we just discussed, the final answer is going to be the maximum of these values. I hope that makes sense, because if you look at the space of all the increasing subsequences, that's your solution space, you have a few that are going to qualify as being the longest, and those are going to start somewhere, and they're going to start at some specific I. So that's going to get captured when we take this max. Okay, so that's where our answer lies. We compute all of these values and take the largest of them. And let's also think about a natural choice of base case. So if we want to think of, again, dp of n, we know that that's going to be 1, because again, this is an array of length 1, so there's only one increasing subsequence, and there's no competition, so its length is going to be 1. So that's a natural base case. So we are sorted in terms of being motivated to figure out what these values should be. We also know what the base case is. So now let's take a moment to think about what the recurrence should be. So remember, dp is a dp based solution is essentially answering two questions: what to store and how to compute whatever it is that you have decided to store. And in this example, we said, well, we are going to store these dp of I values, which were as described, and now we have to think about how to compute them. So let me draw an array out here so that we can stare at what it is that we are trying to compute. So when we are thinking of dp of I, we are really focused on this subarray. The values here are not really relevant at all, because we are looking at a longest increasing subsequence that starts out here. So the rest of the sequence is only going to have values to the right. Okay, so that's already our area of focus, so to speak. And we are already committed to picking A of I. That's just by design, because the semantics was that this is the length of a longest increasing subsequence starting at AI. So given that that's what we are interested in, this element is already in. Now, what would the next element be? First of all, to qualify joining A of I in this subsequence, the next element would have to, at the very least, be bigger than A of I, right? So we can scan the array that is to the right of the ith element and basically disregard all of those values that are smaller than A of I. Those are not of interest to us because they're not going to join our solution because they're simply not eligible. But among the rest, it's not obvious which one should be the next element in our subsequence, right? We should be careful about not being greedy about this, right? So for instance, it's possible that at this point here, you have several choices for elements that happen to be bigger than A of I. And you may be tempted to say something like, let's just pick the first one because that would give us maximum space to build up the sequence further. But it could happen that the first element that you see, the element that is closest to the ith element that's also bigger than it, may be a really large number and it blocks out everything else, and therefore that may not be an optimal choice. But on the other hand, for all you know, it could also be the optimal choice depending on the nature of the input. So all of this is to say that we don't know. We don't know which one of these numbers is going to be the next number in the solution that we are looking for. So what do? In this sort of a situation, we basically go ahead and try them all. And we can afford to do this because of recurrence magic. Notice that because we are starting off from dp of n being the base case and we are working our way backwards in the array, by the time we reach the ith index, the value of dp of j for any j bigger than I at this point is already computed. So we already have the superpower of knowing what are the longest increasing subsequences that start here, that start here, and that start here, right? So we pick up all of those values. And then now we can be greedy because we are being exhaustive, right? So you can pick up all of those values and just take the largest of them, and that would make sense. So let me write down the recurrence and then we will argue that it's actually correct. So here is the proposed recurrence. dp of I is going to be the maximum of j ranging from I plus 1 to n such that A of j is bigger than A of I. It's important that we ignore indices where we have elements that are smaller than A of I because remember we said that they don't qualify. So that's what we are taking the max over. And here I simply have dp of j. So this is going to give me the length of the longest sequence that starts at j, and I'm just going to compare this for all the valid j's that are there. I'm going to take the longest one and use that to compute my solution. Now take a minute to think about whether this is it. Is this what our recurrence is going to be? Or is there something important that we have perhaps forgotten? By the way, what happens if this is an empty maximum? What do I mean by an empty maximum? I mean that there are no indices j ahead of you for which this is true, right? So that means that you're taking a max over nothing. In that case, this whole expression will have to be interpreted as 0 because you're not taking a maximum over anything. So you are not able to extend your array at all, right? So let's actually play out this recurrence as proposed on a small example to get a feel for what it's doing. So this is going to be my dp table. And here is my input. So let's populate the dp table according to this recurrence. As we said, the base case is going to be dp of n at the very end. That is 1. Now, when we come to dp of n minus 1, well, you're going to look forward and you see that, well, you have one element which is in fact bigger than you. So this is a max over one index, the dp value is 1, and so according to this recurrence, we just put down a 1 here. And if you actually play this backwards, you're going to keep getting ones. When you come to 16, what are the eligible indices? Well, we have 3 eligible indices. The max among them is 1, so we get a 1 here as well. As far as 20 is concerned, that works out the same. And as far as 7 is concerned, well, all the indices actually qualify and you still get a 1. So this should strike you as a bit concerning, because this feels like a table that's totally off and is really not capturing what we wanted to capture. And why is that happening? If you've had a chance to think about it, you may have realized that the reason this is happening is because we forgot to account for the fact that A of I itself is participating in this increasing subsequence. So when I'm taking the max here, and for example, you may have caught this in the very first step that we started filling out the DP table. So the moment I go from 36 to 50, what I'm trying to capture is the idea that yes, 50 can be legitimately added to 36, right? And therefore, the combined sequence is 36 followed by 50. So I should really be upping this number to 2, right? Now, when I come to 25, I see 2 options, 2 and 1. 2 is the better of the 2 options. And therefore, my answer here should be 3, because it's 25 combined with whatever subsequence started at the location that witnessed the number 2. And similarly, at 13, we should be upping the number further to 4. What happens when we come to 16? Well, 16 is not compatible with 13, so we will have to drop this DP table entry from the computation, and we have to take the max of these 3 fellows here. But again, we have to remember to add a 1 to that value. Again, what that is signaling is that I can take 16 and I can add it to whatever subsequence I have developed when I was at 25, which is some subsequence of length 3. So I'm going to get a 4 again. And it's going to be the same story for 20. So 20 is not compatible with either 16 or 13, but it's going to work out okay with 25, 36 and 50. So once again, we have a table entry of 4. And as far as 7 is concerned, 7 is compatible with everybody, being the smallest element in the array. And therefore, you're just going to take the maximum value and add 1 to it. And remember that all of these locations that witnessed the maximum actually lead to different solution choices. So in particular, you can combine 7 with 20 and 20 with 25, 36, 50. That would be one solution. But you could also choose to combine 7 with either 16 or 13 and go from there as well. So this is called backtracking, where you try to figure out what were the triggers for the updates that you made in the DP table and walk your way back through the computation to actually build up the solution. So although we said that we are only looking for the length of a longest increasing subsequence, you can actually walk back in your DP table to in fact find such a subsequence that has optimal length. But let's go back and fix our recurrence based on what we just observed. So what we should be doing is taking this max and adding 1 to it to account for the fact that A of I will be joining our subsequence here, right? So that's what the 1 is for. Now I want to spend a moment arguing the correctness of this recurrence. Remember, when we wrote it down first, we had something that didn't actually work when we experimented with an example. And right now, although what we have looks convincing, it's still a good idea to be absolutely sure about it. So how do we show that this recurrence is correct? So how do we go about proving the correctness of something like this? Well, there are multiple ways that you can think about it, and I'm going to walk you through a method that I think is intuitively quite appealing, and it involves proving this equality by establishing two relevant inequalities. Okay, first we are going to show that the left hand side is at least the right hand side, and then we are going to show that the left hand side is at most the right hand side. But what is the left hand side that I'm actually interested in? So what do I want to show? What is the semantics of dp of I? We are claiming that it was the length of a longest increasing subsequence starting at a of I. So remember that that's what dp of I is denoting. So this, just for reminding ourselves what it means, let me call this opt of I. Right, that's what dp of I is representing for us. And what I want to say is opt of I is at most this value that we have claimed on the right hand side, and it's also at least this value that we have claimed on the right hand side. Once we show both of these things, we have the equality. Now, what do these inequalities really mean? When I say that opt is at most max of blah 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 plus 1, what I'm trying to say is that you cannot do better than what we have discovered here. Okay, this is really the ceiling for opt. This is a maximization problem. So when I say opt is at most this, I want to say that there is no other subsequence that starts at a of I that is longer than whatever value we have computed on the right hand side. Okay, so what we are trying to say with this inequality here is that this quantity on the right hand side is the best that we can hope for. So that's what the at most inequality is telling us. What is the at least inequality telling us? Well, I'm saying that opt of I is at least this quantity, which is another way of saying that whatever we have claimed, we can actually achieve, right? I have a witness, I have an actual increasing subsequence that has this length, which is claimed by this expression here. And because of that, I know that opt is at least as good as this, because we at least have this in our solution space. So opt cannot be smaller than this because this is there. This is a witness to this value here. So the second inequality is basically saying our claims are not tall claims, they are actually achievable. So don't quote me on this language, it's a little bit informal, but the idea is to kind of get the intuition across in terms of what are we trying to show. So what we are trying to show is a twofold thing here. One, we are saying whatever we are claiming with our recurrence, we can actually do. We have the evidence that these values are achievable. And on the other hand, we are also being supremely confident in saying that nobody can do better than whatever we have come up with. And once you have both of these pieces of the puzzle, you know that you actually have in your hands the value of the optimum, right? Okay, so let's try to walk through both of these arguments separately. And in this example, these arguments are really quite simple and they should match with your intuition for everything that we have discussed so far. So let's go through it. Let me do the second inequality first, right? So I want to say that you can actually achieve whatever we have claimed here, and the proof of this will leverage an inductive framework. So the base case is when we are making this claim for dp of n. The base case was that dp of n is 1 and the statement is clearly true. And as the induction hypothesis, I'm going to assume that opt of j is at most, let's say, max of k bigger than j such that a of k is bigger than a of j. dp of k plus 1. And so the induction hypothesis is basically saying that this inequality, sorry, I think I wanted to claim the lower bound, so let me change this. This inequality holds for all j that is bigger than I, right? This is going to be our induction hypothesis, and the induction claim is going to be what is written on top, which is that opt of I is at least this inequality. And we want to, of course, leverage the induction hypothesis to show this. So what do I want to show? I want to show that there is a longest increasing subsequence starting at a of I that has this length. So let's go to whatever index j is witnessing the max. If this is an empty set, notice there is nothing to prove, because that means that to the right of I, there is no number that is bigger than a of I. That means that, of course, the longest increasing subsequence starting at a of I is a of I itself, because nothing is compatible with it. But let's assume that there is some j for which we achieve this maximum, right? And the induction hypothesis tells us that, well, opt of that j, whatever j we achieve the maximum at, that is indeed being correctly computed, right? So opt of j was whatever the recurrence told us, and this means that there is, in fact, because opt of j is this value that we have computed, that means that there is a longest increasing subsequence that starts at a of j that has the value that is being claimed by dp of j, right? And because j was something that was such that a of j is bigger than a of I can take this whole subsequence that is witnessed by the induction hypothesis and paste it in front of a of I. That will give me a sequence that is one longer than the value at dp of j and is a valid increasing subsequence starting at a of I. Right? So the optimum length of an increasing sequence starting at a of I is at least whatever is claimed by this, because, you know, I've just shown you a subsequence that is increasing, that has the desired length, and that starts at a of I, right? So that's how we prove the lower bound side of the inequality. Now we want to say that we cannot do any better than what is claimed by this computation here. And this you can argue by contradiction, right? So suppose we have computed something and somebody comes along and says that, no, look, here is a longer subsequence that starts at a of I, okay? So suppose, just for fun, let's say that somebody tells us that the longest increasing subsequence that starts at a of I, this optimum value is 50, but, you know, dp of I was, 42 or something. So you fell short, right? Now, what is the contradiction? What we are going to say is, okay, show me your sequence of length 50, right? Show me your sequence of length 50. What is the second element in that sequence? It must be some aj for j greater than I, which means that dp of j should have been 49, because if I chop off the ai element from your 50 length sequence, right, if I just remove that, then what am I left with? I'm left with a 49 length sequence that starts at some a of j. But by the induction hypothesis, I know that my values are being correctly computed for all j that are bigger than I. So when I would have run through that specific j, I would have pulled out a value of 49. And so when I take a max over a bunch of numbers that involve 49 and 42, the max would not have returned 42, it would have returned 49, right? So that's the fairly straightforward contradiction here, right? So if somebody gives you an optimal solution, just break it up into its component pieces, in this case, the first leading element and the rest of the sequence. And the point is that the length of the rest of the sequence is correctly captured because we have this ammunition from the induction hypothesis. And since that is correctly captured, we cannot actually do better than the calculation here, because any optimal solution will actually basically fit into this framework, right? So that's that's the intuition for why the upper bound also works out, right? So whenever you have a recurrence, I think this is a nice way of thinking about it. First, make sure that whatever you're claiming is realistic, that you can actually achieve it. And the second aspect of it is to say that nobody can do any better than the outcome claimed by your recurrence. And to show that, typically you will take a hypothetical optimal solution and break it up into two parts in a way that the two parts combine based on the calculation in your recurrence, and the correctness of the individual parts comes from the induction hypothesis typically. So I hope that notion of how to prove the correctness of a recurrence made sense. We will not be going into this level of detail when it comes to proving the other recurrences that we set up for the other problems this week, but I would still encourage you to follow up on the recurrence relations that we write down and convince yourself that they're actually all right by following this framework. We will, of course, convey the main intuition for how we come up with the recurrences, and hopefully that'll be enough information for you to complete the proofs when you actually sit down to do them by yourself. So in the next video, we are going to talk about a problem called subset sum. So this concludes our discussion around longest increasing subsequence. We have some fun problems in the assignments that build up on variations of this problem, and I hope you have a good time working through them. And I'll be happy to discuss them with you when the time comes. But in the meantime, let's move on and talk about subset sum next. I will see you in the next video.